hi everyone. This is Open Cloud Research Jam number 7. Is actually almost exactly a year after we did the first one. So it's amazing that people are still here. We have 3 presentations today. So already did his. And today we tried a new experiment. In the beginning, it took probably a little bit too long, over half an hour of what we call open mic, that anyone can share a small snapshot of results. So for those who are watching this as a recording on YouTube, you missed that part. And I am, yes, deliberately trying to create FOMO for you. So next time, try to join in person. Cool. Okay, with that, we can get started with our first presenter. I think Rob is our first presenter. Let me make sure. Yes. So whenever you're ready.
Hello, everyone. Thank you for having me. I'm Robert. I'm a third-year PhD student from Berlin, and I'm mainly working on meta-learning. But today, I want to talk about sort of a pet project of mine, on which I've been working on for a year. And it's called evosax, and it's basically a JAX-based library of evolution strategies. And maybe up front, a little bit of a warning, this is not a full JAX talk, and this is not a full evolution strategies talk, but I hope I can nonetheless sort of motivate why JAX is sort of the perfect counterpart for modern day evolution strategies. So let's get started. What is an evolution strategy? So I think all of us know that the workhorse of deep learning is gradient descent. And gradient descent is awesome if we're working with differentiable objectives and sort of the function which we're trying to learn is end-to-end differentiable. But this, in some cases, can limit what we're trying to do. So think of non-differentialities, like, for example, spiking in neural networks or hard attention. These are usually not differentiable, and in these cases, the deep learning community has developed tools such as a straight-through estimator or some form of surrogate gradient that can sort of try to fill in. But in these cases, you're not really working with a true gradient, but you're working with a substitute. And the promise of evolution strategies is that it might be able to help us overcome some of these limitations. And instead of working with an analytical gradient, evolution strategies work with a search distribution, and they can be applied to basically any form of black box optimization problem. And the way how we would proceed here is we would generate essentially a set of candidate solutions. We would evaluate them and on some form of fitness function that we're interested in. Importantly, this fitness function does not have to be differentiable. And then we would update our search distribution according to essentially the information that we had gathered before. So this feels already like something some people might be familiar with in the forms of Bayesian optimization. And essentially, the problem of modern day evolution, this is like an example for how such a search strategy could change over time. So what you're seeing here in these contour plots is essentially a multivariate Gaussian, like a 2D Gaussian, which tries to find the optimum in form of this star, and you can sort of see the function evaluations on top. Okay, so let me continue with what is the problem of modern day evolution strategies. So instead of running a forward pass and then a backward pass to compute gradients and update the parameters using, for example, Adam or some SGD variant, we sort of rely on these population evaluations, right? So our evolution strategy would tell us, hey, these are candidates and we're interested in evaluating them. And now if we wanted to evaluate them, we would somehow have to do this in parallel if we want to sort of not slow down everything to sort of evaluation sequentially. And usually in order to get a good estimate of what the fitness of one population member is, we would not only do this once, but we would do this multiple times, like for example, on multiple batches or on multiple sort of stochastic rollouts of a policy. And the way how people have commonly done this is by using some form of multiprocessing, right? So in this case, each sort of rollout would be dedicated to a single core on your machine, and then you would run the rollout to estimate the fitness. Or you would use some form of task manager where you would have maybe multiple hosts and then sort of have to orchestrate how to collect the information. And you can already see that this sort of requires some form of engineering. And one sort of limitation of this, or some conceptual background, that I felt sort of appealing, or was appealing to this problem, is the hardware lottery, which was sort of put out by Sarah Hooker, I think 1 or 1.5 years ago, which basically states that oftentimes there are research ideas which sort of succeed in one form or way, so in terms of adoption maybe, because the hardware and the software stack that is currently available sort of is very suited to promote these ideas. But there are also many ideas that are not sort of tailored to it, our modern day hardware stack. And these sort of, fall into a very quiet graveyard where sort of they are not picked up on. But every now and then we have a change in our hardware stack or in our software stack, and these ideas might sort of be able to be picked up again. And I feel like JAX is sort of one of these developments in the software stack that might allow us to sort of, make evolution strategies more popular than what they are nowadays. And what I mean by that is JAX is essentially a library of function transformations, which allow us to speed up certain computations using JIT compilation, or allow us to compute gradients, or allow us to essentially map function evaluations. And this mapping can be done sort of in an auto-vectorization fashion, or it can be done across devices. And what we can then sort of do in the context of evolution strategies is, instead of using CPU-based parallelism or DASC, we can make use of modern-day accelerators like GPUs or TPU pods. And what I'm trying to convince you, or I'm skipping a little bit, is that this is really very simple, and these mapping primitives make it possible to essentially have evolution strategies drive. Okay, and I sort of came across this like more than a year ago, last February, and wrote like a little blog post about how one could evolve a pendulum controller, like a small NLP, using this form of vectorized evaluations and JAX. And after that, I started sort of working on implementing a bunch of evolution strategies in JAX. So in that blog post, I only looked at CMAES and put them into a neat package called evosax. And this, what you can see here, is basically the simple API of evosax. You would import an evolution strategy, for example, CMAES. You would instantiate the strategy, set some hyperparameters, initialize its internal state, and then you would follow a simple ask and tell sort of API for asking for new candidates. Then you would have implemented an evaluation function using these map primitives yourself, and then you could tell the strategy and it would update. And basically all of what's sort of important internally is stored in this PyTree state, and you can explicitly control for the hyperparameters, sort of like a learning rate. And then evosax implements essentially a set of different evolution strategies, which are all sort of compatible with the internal workings of JAX. So these mapping primitives and JIT compilation and fast compilation using, for example, scan primitives. Okay, and you can see we have a bunch of different sort of old school evolution strategies in the form of, for example, particle swarm optimization, but also sort of methods which are being used more in neuroevolution like CMAES or augmented random search, and even sort of tools which were developed in the context of meta-learning like persistent yes. Okay, just a couple of features of what this enables. So one thing that this enables is vectorized evolution strategy rollouts. So for example, if you're interested in not running a single evolution strategy, but sort of running multiple evolution strategies in parallel, where you have different hyperparameters for the different strategies. So what I'm showing you here is basically if you wanted to run augmented random search simultaneously or in parallel using 3 different learning rate decay factors, then you could simply sort of define them as an array and then map over the dimension of that, that array that you're interested in. Okay, and this would use this vmap primitive, for example, but you could also use pmap instead, and thereby not auto-vectorize, but parallelize over devices. Okay, another set of utilities that I've implemented are sort of standard fitness shaping transformations where oftentimes in evolution strategies, you don't really want to work with the plain fitness score that you might get, like for example, the policy return, but you would want to use some form of normalization to stabilize the updates. Anyways, these are details. This again is all JAX transformable, so jitterable and mappable and accelerable, so can be run directly on the accelerator. I've also implemented utilities for essentially reshaping parameter vectors. So evolution strategies work on flat parameter vectors oftentimes and have to be reshaped into sort of pie tree like dictionaries, which can then be used to compute forward passes to the network which you're trying to evolve. And I've basically implemented a set of tools for doing this reshaping also in a parallel fashion so that you can do this basically all simultaneously on the accelerator of your choice. And you might have seen evosax before. So basically simultaneously while I was developing this, David Ha and his colleagues at Google Brain sort of developed a separate tool called evosax. And evosax is awesome. And what evosax focuses on is essentially the hardware accelerated part of the evaluation of these population members. So evosax, when it originally came out, didn't have that many sort of evolution strategies, which I have been focusing on, but implemented a bunch of tasks, like for example, the rollout of workers in BRAX, which is this JAX-based continuous control package, or endless sort of classification tasks. And what I've been doing essentially during the last couple of weeks is try to marry it, basically the benefits of evosax with evosax, and the team of David Ha, Eugene Tang and others have been really, really helpful. And basically this has led to me providing essentially the backend for many of the evolution strategies in evosax using evosax. Okay, so here you can see sort of two examples of two merged pull requests where we're now integrating augmented random search and OpenAS from sort of evosax in evosax. Okay, yeah, so I'm also providing simple sort of flash network wrappers and some problem rollout wrappers, not as extensive as evosax. And I have been looking into sort of tuning the default hyperparameters, because I feel like oftentimes we're ignoring how important the amount of compute and sort of graduate student descent that went into the tuning of the hyperparameters that we're using in, for example, in Adam and so on. And things like the Kapati constant for the learning rate of Adam and so on are real sort of phenomena which are important for a technique to be adopted. And I've been sort of spending some time on cross-validating and grid searching over these things to make it easier for people to get into evolution strategies. Yeah, and maybe just to wrap up, I showed you sort of a little bit of evolution strategies. I showed you what evosax implements in sort of the diversity of the strategies and these small utilities. In the future, I would like to or what I'm currently working on is adding restart wrappers. So oftentimes when an evolution strategy converges, what one does is one sort of restarts the evolution strategy by sort of scaling up the variance or these things to see if this is a local optima or if you can sort of find a better global optima. I want to implement batch wrappers so that you can roll out multiple evolution strategies sort of collectively. I want to add more strategies, tune the default hyperparameters, and so on. And sort of just to sort of share some research ideas or what fascinates me about evolution in JAX is sort of this aspect of very simple auto-vectorization of multiple ES. So having multiple ES run in parallel with different hyperparameters. And so, for example, what I'm showing you here is one strategy where essentially I mapped over 2 dimensions of hyperparameters. So this differential rate and the crossover rate are just 2 hyperparameters for this differential evolution strategy. And using a simple VMAP over this, you can sort of run multiple, you can run all of these 100 evolution strategies in parallel over a problem and sort of see how the fitness shapes changes over the generations. Okay, and the last thing is sort of something for the future as well. usually we think of a single evolution strategy and sort of using it as a black box optimizer, but of course we can also have multiple ones of sort of hierarchically stacking them together, right? So you can think of sort of having multiple instantiations of evolution strategies with different hyperparameters, and then having a meta controller that essentially collects the data from all of these strategies together and then updates sort of the hyperparameters. And this is sort of going back to, I guess, the Schmidt-Huber-esque idea of meta evolution and sort of having these self-refining systems that improve upon each other. And yeah, with that, I conclude. There are, maybe I can show one last thing. I have put, can you still see my screen? Can you see my groove? Yeah. Okay. Yeah, I've put together a bunch of collabs working through sort of how to get started, and in the Discord afterwards we can walk through this together, and I can show you more details about how to get started with this. Yeah, that's it from me. Thank you very much.
It's beautiful. It's really nice work.
We can maybe take a few questions. So I have one. The ask, was it ask, show and tell, or ask, evaluate, tell design? Is that part of what evolution strategy is about, or did you come up with that? And does that sound like? Yeah.
So in general, this is sort of the API of most hyperparameter optimization tools that are out there. Like, for example, Meta has this library called Nevergrad, or David Ha had like a evolution strategy package, ES tool, and they all sort of follow the similar API. And I think also Bayesian optimization tools mostly have that. And I kind of stuck to that because that's what people might be familiar with.
And even though it sounds like it is a loop that's going to be executed sequentially, I mean, in practice, you can ask and get I've got a whole population of candidates. Is that what you
exactly
do in practice?
Exactly. So so in general, like the evolution strategy field out there sort of divides into types of evolution strategies which use a form of finite difference estimator. So maybe a little bit related to what was spoken before about, like with these forward gradients, which also use sort of random perturbations, right? And evolution strategies like CMAES, which have more explicit models of sort of the loss surface, which you're trying to optimize over. And yeah, like you said, you can, in general, when you ask, so I think I showed really briefly, when you instantiate the strategy, you set a population size, and then when you ask for candidates, you get as many candidates out as the population size that you set originally. Yeah. Let me see if there's a question in the messages. I don't think. Thank you, Esla.
We should probably move on to the next speaker, but right before we do that, we didn't take a picture yet. Oftentimes we kind of take a group photo. So if you're comfortable with it, turn your camera on and wave. If you're not comfortable, totally cool, of course. And I'll take a screenshot here. 5 seconds, 5, 4, 3, 2, 1. Keep waving, keep waving. One more. Someone's not smiling.
This whole thing's gonna be on YouTube. What's the point?
Okay. Well, who's gonna watch this whole YouTube? Anyway,
that's true.
Thank you for waving, everyone.
Show YouTube.
We should go on maybe with Edwin.
Yeah, and also we're doing so after presentation there will be a hangout session on Discord. So if you have more questions for Rob, you can switch to his voice channel, which is already created.
Awesome. Edwin, take it away when you're ready.
Okay, yeah, so my name is Edwin, and I'm currently student in National Yangming Jiaotong University in Taiwan. And I want to introduce everyone to this project that I have been working on kind of for the last few months, 2 months or something. I call it Retrieval, and it means Retrieval Enhanced Transformer for Vision Recognition. And Well, so in the last few years, there's been a lot of talk about transformers. Basically, they have been the state of the art for NLP since they came out in 2017 with the original paper. And then we have had quite a lot of like progress from papers like GPT and BERT. And well, then eventually there's been like all of this trend of scaling, which has led to like things like GPT-3. And similarly for computer vision, also there's been like a huge trend of also like scaling, um, especially in the last since 2020 already. We have had the vision transformer, and then since then there's also been like quite some trend of like implementing some of these ideas of transformers and modeling of images as a sequence for computer vision. And I think one of the reasons why transformers have been like widely adopted and they have been extremely successful in the past few years is mostly also for the same reason that Rob just mentioned, the hardware lottery. Basically, they are actually really suitable for our current accelerators like GPUs and TPUs. So they are highly parallelizable and they can exploit computation. And also another reason is that they can manage a variety of data types. Um, but today I want to like talk about like one in particular that I think it's like very interesting. This is a paper pretty recent. It's from DeepMind and was published kind of already like 3 months ago or 4 months ago at this point. It's called Retro and it means like Retrieval Enhanced Transformer. And I think it's like this paper is pretty significant because basically they prove that by enhancing like a transformer input with retrieve neighbors, they can actually outperform much larger models. In particular, they use a model that has 7.5 billion parameters and has like 2 trillion and retrieve from a data set of 2 trillion tokens. And it can outperform like much larger models like GPT-3 and Jurassic 1 with 175 billion parameters, or like another model called Gopher with 280 billion parameters. So that's like pretty impressive. And the way that it does it is by retrieving from a large corpus based on neighbor similarity to enhance the input. And the idea is like pretty intuitive. These are some slides that I include the link here. It's called like this. It's a blog post, illustrated retro, and I think the main two ideas is that basically that this kind of model actually separates the language information from the word knowledge information. So in the past, large models like GPT, it would have to know how to like use the language, but it would also need to learn a lot of things like what's the name of the first president of the United States, or who won like a certain like MLB like championship in a certain year. All of these things are stored in like the parameters of a large model. But by actually doing retrieval, you can explicitly separate this language information from the word knowledge information. So it basically makes for like more efficient use of parameters for encoding language. And the way that they do it is actually pretty simple. Basically, they start by doing a retrieval of certain like query. For example, in this case, they use the example the Dune film was released in. And basically, based on that, you would like pass that query through like a pre-trained transformer, in this case, BERT, and then they would use this query to search a large database, and then to get some like their nearest neighbors. In this case, something like Dune is a 2021 American epic science fiction, or something like Dune is a 1984 American epic science fiction film. And basically, then they would like take these neighbors along with the original query, and they will pass them through a transformer. In this case, it follows like an encoder-decoder architecture, and by this way, it would actually be able to like do better like language generation. And this model actually, well, then they also like use it in a lot of downstream tasks, and it obtained like very good results. So my idea was pretty simple. It was basically like grabbing the similar concept, but applying it to computer vision. And this is like what I call like retrovisor. Basically, you also start with like a query image. In this case, you can see it's something like this, like a rear view mirror. But if you pass this through like a CNN or a BIT, current models probably would predict from this model, it's probably like an airplane because, well, we see clearly an airplane like takes a large part of the image. But we as humans, we know that actually it's not only like an airplane, but rather like what we want to focus maybe is like the object, like the mirror itself. But like the current models probably like are not designed to deal with this kind of uh, examples. So what we do is that actually by retrieving like from similar features that we basically pass our query image through a feature extractor, which can be anything, a CNN or a BIT or any kind of uh, image recognition architecture, and we will like retrieve neighbors, and then we can retrieve something like this and this that are other images of like rear view mirrors, but in different situations. And then we could like combine this information, pass them through another transformer, also following a similar encoder decoder architecture to basically like accurately predict like the class for this kind of image by actually encoding information from like similar pictures and combining it with the original query image. So this is like the basic idea behind this project. There's a lot of details in terms of how do you actually want to combine this information. In particular, there's this model, which I call NEAT, and means Neighbors Associational Transformer, which would first like work only with the neighbors, and then it would like combine it with the image. So basically right now it's separated into two stages, like one stage for only neighbors, one and also for only for images, and then there will be like a stage on that combines like the information from the images and the neighbors. But actually these are all design choices. You could also like do it in like one single stage and combine it like all together. So I have been doing quite a few experiments in the last few months, and it's still something ongoing. But also there's like other questions like how do you select your feature extractor, or like maybe like how large are do these models, like is there like some sort of ratio of like how should they be, like which part of the model actually is the most important, like where should you like spend most of your computation to get better results. And also questions like do you need like the whole set of like features from the images, or would you just like be enough to use, for example, like one set of pulled features for like this whole image? These are all design questions that I think are like worth investigating, but that's kind of like the general idea. And the idea would be to definitely focus on, okay, basically getting like better classification results. But aside from that, there's also this particular follow-up application that I'm also interested in. Um, I don't have a lot of experience with generative models for computer vision, but maybe someone in here could also like be interested in this idea. Basically, it would be like the same, but instead of having like a head that would be for classification, you would use this to actually like do some generative modeling. In this case, it's colorization. So you would start with like a gray or black and white or grayscale image, and then you could like pass it through a feature extractor, obtain like similar images from the database, but actually in color. And that way, like we could like more effectively like colorize the image by having like explicitly some pictures of whatever you want to color that are actually similar and could actually like guide the colorization process. Um, so I think this is the like the like the main idea of the presentation. And as I mentioned, I also prepared a few like follow-up slides. But I think yeah, that should be it for now. And then let's, if you have any questions, just let me know.
Just maybe a very basic question about retro itself when it applied to language. Is it essentially just like a way to do a smarter prompt engineering, you think?
Well, To be honest, I'm not that familiar with language, so I'm probably not qualified to answer that
Okay. Sounds to
question.
me, I don't know, if anyone of you know, sounds to me that usually you have one input and you get output of that. But what Rachel does is it searches the database and augments your input by adding a bunch of other things. People also do that manually, and they call that prompt engineering. Basically, you have a longer prompt along with your input, and then to get the intended output. I wonder, but it wouldn't be just prompt engineering if they also involved this process in training, which I'm not sure if they did.
The thing is that about Retro is that actually they build up on quite a few ideas. In particular, there was, I think, this other paper, I think already from 2018, which is called KNNLM, which it takes this idea, but it doesn't actually train the model end to end. And I think this is one of their things that distinguishes them from like previous work, in the sense that basically the whole thing, like with the neighbors, is like trained end to end. The neighbors pass through like a small encoder that follows like, yeah, it's like basically like a transformer encoder, and then the query is like passed through like a decoder, and then it will like do like cross attention. Specifically, they propose like this chunked cross attention mechanism for doing like cross attention to the encoder um values and keys. Um, so in that way, if we actually think about it, okay, maybe like this is something, maybe like could be like thought about some automated like process of like prompt engineering, or because at the end what it's doing is just adding like some additional knowledge or some additional information to your like input to actually guide your model to like get a better output, or that's the way I see it.
Any other questions? We probably can take one or two more.
Okay, so
Yeah, if not, you can
set of
try.
neighbors will probably be quite noisy. Um, yeah, like actually regarding the neighbors, I think that's like a really good, interesting question, because in the case of well, language, as far as I know, like language, like you wouldn't like do some transformations like we do in computer vision, where okay, we actually augment the images and then there will be like some heavy augmentations. And that's something that I included in these backup slides, but just to like illustrate the process. This is, for example, I have been working on this anime dataset, and this is like a commonly used augmentation that is called mix up. Basically what it's doing, it's combining like two like images together kind of, and this one is called cut meets, and it also does something similar, but basically it's by doing some cuts. And the problem is that these kind of augmentations, they are probably, you can think intuitively, they are not compatible with retrieval, because if you actually try to do retrieval for something like this, you are going to get something that is neither the image A or image B, and therefore the choice of how do you actually choose neighbors and what kind of augmentations are actually valid or suitable for this kind of method are like a really important like question that I'm actually kind of have been working on. Um, at least from what I have seen, even like some of the most simple augmentations that you would do some random cropping can be like pretty destructive for this method, because intuitively you can think that if we have something like this, which is a face, and you do some like aggressive cropping, maybe like you're going to end up with like an area that is unrecognizable, and therefore the retrieval results, the neighbors are going to be noisy, and therefore you are going to be inputting noise, and we know that garbage in, garbage out. So that's been one of like the largest challenges that I have been facing while training this kind of model, is that most of the augmentations that probably people would use for computer vision are not so suitable for this kind of architecture. So how do you evaluate it in a way that it's kind of fair for well the current architecture and the previous work in a way that, okay, it's like reasonable. That's also like a question that I have been asking myself. But yeah, like the neighbors are like quite a huge problem. There's also like other problems, like how do you choose like distances? Like for example, right now you can use like L1 or L2 distance to see like how can you like choose like the appropriate neighbors. But that's also something that I don't really have like a solution right now. It's something that I have in my to do, basically actually making sure that the neighbors that you're getting are actually related, because sometimes like the way I'm doing it right now is pretty manual and it's definitely not efficient. But I have been working on this kind of by myself, so I don't know, there's been a lot of things that I have been trying to fix up. But yeah, that's kind of like the next step would be to actually inspect the neighbors to make sure that the data that you're inputting into the model is clean and it's actually something that you can get like, let's call it a good signal to noise ratio, because if your signal to noise ratio is very low, then the training process is not going to go well. So yeah.
Nice. Probably we should move on. We're a bit over time, but I think we can get through the last talk. So Jean-Michel, am I saying your name right?
Yes, it's
okay.
good.
Perfect.
Okay, so hello everyone. My name is Jean-Michel Amatsar. I'm a PhD student in Sorbonne University in France and Charente Diop University in Senegal, Dakar. And this is joint work with Sri Harsha Atwa and Yash Sharma. Oh no, this is not the correct work actually. It's this work. Okay, so we are interested in bounding the out of distribution risk. So let's start with a few words on out of distribution. So basically, when we do deep learning or machine learning, we are used to having the training and test data to come from the same data distribution. And here we are interested in a situation where the test data will shift. So the test data can shift in many ways. It can shift due to corruption in the way the data was collected, but it can also be due to natural shift. So as an example, I've provided here two examples. One is from Hendricks and al. So they have taken ImageNet and CIFAR10, and they have corrupted it with 15 corruptions, so Gaussian noise, shot noise, various kind of noise. And the goal is to learn on the native data set and to try to generalize to all these new corrupted data sets. Another initiative is the WILDS benchmark, which is a collection of data sets. Here I have displayed just one, that is the Chameleon 17 dataset. Basically, it's a dataset that is used to predict whether those patches have a tumor or not for breast cancer. And so basically the data have been collected in different hospitals. We are 5 hospitals, and the goal is to learn on 3 hospitals and to generalize to the other 2. So, okay, so now we are interested in bounding the OOD risk. But first, let's understand why it is important. So when we deploy a model in a new environment and the dataset shifts, we want performance guarantees with uncertainties. And so this is what we are interested in. Or we want to know if we want to label so if we are in a situation where we have a bunch of new data that are unlabeled, we want to know if we should label them or not. So there have been 2 lines of work in this. The first line of work is domain adaptation. And the second line of work is trying to predict the OOD risk directly. So basically here we just want to bound the gap between the target risk and the source risk. So the term on the left is the gap between the risk on the target distribution, so when the data has shifted, and the source distribution where we have labeled data. And domain adaptation have provided bound with a function, a distance function between the unlabeled target and source distribution, and another function another function of the labeled target and source distribution. And the second line, do not use the target labeled data. So basically these bounds, the domain adaptation bound were found by Ben David et al. In 2006, and it has been generalized. It has been generalized later by many authors. Here I provide just two of them, Zhang and Acuna. So basically, Ben David has provided this bound for binary classification, and Zhang proposed to generalize the same bound for multi-class classification. And instead of using the L01 loss, he has used the margin loss and score function. So it was a notable generalization. And Acuna later generalized the same bound. So the bound doesn't change, just we generalize it to other cases. And so Acuna provided the same bound, but with the divergence coming from F divergence. Okay. And the second line of work, do not use the target labeled data. Instead, they are directly trying to predict the out of distribution risk. So what they do is that they are trying to estimate the gap directly with a function of the source data, the source label and unlabeled data, and the target, the unlabeled target distribution. So what they do is that they provide an inequality. So here I've written it in another form. So I've provided here an inequality and an epsilon term that is just to model the error or the uncertainty. And both of those, so I've mentioned just two methods. Both are very recent, one from 2021, and the second is going to be published at iClear this year. And so both, they are not using unlabeled data from the target distribution. And they are both using confidence. So they are confidence-based method. So confidence in the output of the network. So what we are interested in is how tight are these bounds experimentally. And the one question we have is, do we lose tightness by not using labeled data? And is there a trade-off here? So can we benefit from labeling a small fraction of the target data for the target distribution to get tighter bounds? So we have not included here, but we have our own functional that is a distance between data sets. And so as an experiment, we have tried to plot the distance between the source distribution, which is here in the lower left corner. And so every dot here is a data set, is a data distribution in a sense. And the farther we are from the identity data set, the greater is the gap between the target and the source distribution. And this is expected. So in a nutshell, if you have one training data set and your test data set is very different from your training set, you are expected to have your accuracy to decrease substantially. So in this first experiment, we have used MNIST and MNIST leftover, which amount to 32 domains, so 32 different data sets. And we have provided this, this plot. And in a second experiment, we have worked with CIFAR10C. And here again, we have this, this linear plot. And okay, so it is work in progress. Now let us, we will now discuss what we want to do in this research going forward. So we plan to add other methods from the literature for comparative analysis. The other methods have been presented before. And we want to add a dispersion metric to rank methods according to tightness in the performance gap. So basically, what our idea is that for each method, we are going to have this kind of linear plot. And our so what we think is that the tighter the data points are to the so the lower the dispersion between these data points, the better. So in other words, the less the variance, the better the quality of the functional. And yes, so this is what we want to do. We want to compare many of these methods, and as a final study, we want to also study the effect of using labeled data or not. So do we have an advantage using labeled data, and how much is this advantage compared to not using it, as other methods like this one are doing? So yes, and so this is what we want to do. I want.
Jean-Michel,
Yes?
can I ask a question? Maybe I missed it. What's your functional here? What's your data set distance?
Oh, I have not included it here because I just for the sake of brevity.
Okay.
But basically, this is a distance that use label data. It is a kind of functional that comes from domain, that is inspired by this distance, these results. So we use the label data from the target distribution, as opposed to these methods that do not use it. But these methods do not try to compute the uncertainty. So their approach is more to compute, like to predict the out of distribution risk. And we want to have like one big set of methods and just try to compare them on the basis of the dispersion metric. Yes, so
okay.
So that is what we want to do, and so the goal would be for the practitioner, when he will be so the practitioner with his trained model, deploying it to a new data set. The goal would be to estimate the gap, the accuracy gap he might have with uncertainties. So this is what we want to do, and we want to provide them a tool to know if they should label a little bit of the new data, and how much new data should be labeled in order to have an accurate uncertainty estimation of the gap, the accuracy gap. Yes. So basically, this is what we want to do. Okay. So thank you. This was it. And yeah, if you have a question, I would be happy to answer it.
Maybe we could take one or so questions, and then we can all pop over to Discord, and then we'll have more time to talk about more time for in-depth questions.
I think I have one question. I think it's the same as what Jason was asking, but it's still not clear to me. How do you define the data set distance? Is it like distance between the covariates or between labels?
So so basically there are many. So there are two kinds of approach. In this first kind of approach, the approach from domain adaptation, they are using a distance between unlabeled data. So they are computing a distance between the unlabeled source data and the unlabeled target data. And the first distance that was proposed was by Ben David, and it is a distance based on the total divergence. So this is like a functional to compute the discrepancy between distributions, and they have extended it to data sets and to unlabeled data sets. And other people have extended the first divergence that was the total divergence to F divergence, which is a more general class of divergence. And then other, yes, so this is a distance between unlabeled data. But to completely bound the risk, we should use labeled data. And in the literature, there are other methods that are here to compute the distance between also labeled data. And here we want to compare every flavor of distance between data sets to basically to bound the risk between the target and the source data. But in this literature, you have like in each of these papers, you have a different distance between data sets. And here our functional, so we have not presented it, but our functional is taking into account so it is computing the discrepancy between two labeled data sets. And we hope that by using label, we are going to have tighter bound here. So this is why we do this comparative analysis. We want to do this comparative analysis.
Perfect. I think with that, we should probably wrap up this call, but we can all pop over to Discord. On Discord, there are channels for
each of
these talks. Roseanne, what are they called? Oh, they're just under Research Jam with the name of the
Research Jam was the presenter's name.
Perfect. All right. So thanks everyone for coming. That was great. Thanks to the presenters. Give the presenters a quick round of applause. And see you on Discord.
Bye.
Yes.